This video is not a theory about how the pyramids were constructed. It is about how I would have built them had I been the chief engineer using only the materials available. That is, wood, rope, and stone, and maybe a little copper and iron. My interest in this subject was piqued by a video I watched a few months ago by David Childress about Peruvian megalithic structures like Sacsayhuaman, where stones weighing up to 125 tons were fitted one to the other with great precision. He said something I thought was rather pithy, that they used such large stones because it was easy for them to do so, and if it were really hard, they would have used smaller stones. So any construction techniques I might have employed would have been those using the least amount of energy. For the pyramids, this rules out ramps. Let's see why. The absolute minimum amount of energy needed to construct a pyramid is more than the measure of the potential energy put into the stone blocks by lifting them up through a gravitational gradient. If we drag a block up a ramp, we invest potential energy into the block by raising it, plus the potential energy of the men who went up with the block, undoubtedly at least doubling up the energy of the block, plus the potential energy of the ramp material that had to be raised up, now perhaps tripling the energy total, plus the potential energy of the men who went up to drag the ramp material up the growing inclined plane. That's probably quadrupling the minimum energy required. Then we have to dismantle the ramp, and men have to once again climb up and climb down, towing rubble on a sledge. That would surely quintuple the minimum energy required. And then there's the friction from dragging things up the ramp. So let's sextuple the minimum energy requirement. And I think I'm being extremely conservative here. Clearly, if we don't build the freaking ramp, we save as much as 75% of that miserable total. And if the fewest possible number of men go up on top of the pyramid site to work, we save another large percentage, leaving us much, much closer to the ideal total. Manhandling blocks up ramps is therefore unacceptable. What a relief this is to the poor fellows who would have to haul 2.5 million 2.5-ton stones up a 7-degree incline in 110-degree heat. Let's face it, they'd drop like flies from heat stroke. The death toll would be staggering. There are schemes using levers that use close to the hypothetical minimum energy. People climb up a distance and use their body weight to cancel the weight of the stone, and up it goes to the next level, while they come down and have to reclimb to reset the lever. The net total weight raised is then just the weight of the stone. The energy expended is equal to the potential energy invested in the raised blocks, plus miscellaneous wasted energy. However, if they come down each day, then climb back up, we start multiplying the miserable total once again. One drawback of all lever systems is the multiple handoffs to the lever at the next level. And you have men at every level of the pyramid standing out in the hot sun all day long. If they want to take a break, or if they need to take a dump or a piss, they have to carry a pot to pee in, as well as their food and water for drinking, and carry it all down at the end of the day. God help you if you break an arm or leg up there. There would be hundreds of men on the flanks of the pyramid all day long in the 110-degree heat. You're going to have fatalities. Remember, it's a 52-degree incline, easy to fall a few stories or more. Since this is my pyramid, I won't have my guys dying like that. They'd kill me. I want them all as comfortable as possible, while still getting the job done on time. The only idea that showed any promise of accomplishing my ends of least energy and discomfort was that proposed by Franz Luhner of Germany. His system drags blocks up the finished side of the pyramid on wooden tracks. His is an extensive site, and I encourage anyone interested in pyramid construction ideas to spend some time here. I also found Robert Hartranft's site. He proposed using a long rope and pulling from the opposite side of the pyramid at ground level to get a block on the other side to go up and over to be released at its appointed destination. His site isn't as developed as Luhner's is. On the other hand, His workers don't have to spend time on the hot flank of the pyramid. And I found this picture in a religious video, but I don't know who to attribute it to. Any number of people have thought of pulling blocks on wooden sledges along the flats on a slick wooden train track thingy. There are demos on the internet of such tracks in action, and they appear to be 6 or 7 times easier to use than just hauling along on dry sand. Using wooden tracks is a no-brainer here. However, I had to make fairly extensive modification to Lunar's rope roll technique in order to get it to work easy on my men. I took everybody off the side of the pyramid and put them either on top of the pyramid work site setting blocks or at the bottom pulling the blocks up the side. Only track construction, inspection, maintenance, and repair personnel would have to be on the flank of the pyramid, and then only in small numbers. And they would never have to climb up a ramp, at least not when it gets higher than about 10 feet. I send my guys up on elevators, using the same technique used for the blocks, except now they are raising blockheads. That's what my work gang is called, the blockheads. That's because you'd have to be a blockhead to work on any stupid pyramid vanity project. And that is all it is, a vanity project. Some historians assert that because the ancient Egyptians did not use the wheel, they didn't know how to make one. This is like saying they didn't know where babies come from. Of course, they knew what a wheel was. Here's absolute proof that Egyptians at the time of Giza knew what a wheel was. These are screenshots from an excellent National Geographic documentary about Jean-Pierre Houdin's theory that an internal ramp was used. I don't agree with Houdin, but it was a great documentary. They're excavating where the workers lived who worked on the pyramids at Giza. Can you see the proof? Yep, it's that pot. This was made on a potter's wheel which was in use in Mesopotamia at least 5 centuries before the pyramids were built. See the wheel? See the axle? The bearing was a little rock under the big wheel. It works as a flywheel, and you spin it with your foot while you work the clay with your hands. The official explanation for this pottery is that the Egyptian potters used their kids, who spun around with the clay on their heads while their fathers worked it into a pot. Thus they were the first potheads. I can't buy this official story, so instead I'm proposing that they just use a standard pottery wheel. That's wheel as in wheel of fortune. Wheels were certainly in use elsewhere before the pyramids were built, but the Egyptians didn't need them because their country is only 2 miles wide and the 600-mile length has a liquid highway. There was no economic incentive to develop a regular highway system. The Egyptians didn't need roads because they had boats. Their oxen or donkeys dragged their produce to the riverbank on a sledge or travoy, and they loaded it on a barge. I'm sure they had taxi boats as well to take them to Aunt Marge's place on the other side of the river. And they didn't have any wood, unless it was imported, no trees. A wheeled peasant's cart would have been a needless expense, and wooden wheels break on rough surfaces, and springs are nice and shock absorbers, and the axle has to be constantly greased, and you can't haul large blocks on primitive wheels anyway. They'd just break right away, or the axle would break. But I need a wheel. So I took Franz Lunar's rope roll idea and expanded it into a full-blown wheel. Since I don't have to impress Egyptologists, I can use a real wheel on my pyramid. Egyptologists are universally opposed to the wheel because they can't find evidence of it in that time period. They must therefore take the logical position that the ancient Egyptians were simply too stupid to think of the wheel as even a bearing, let alone as a mechanism of transportation. People who did fine work like this couldn't imagine a wheel. Here's 2 guys, Boo-Boo on top of the developing pyramid, maybe 40 feet up, and another guy, Beatty, on the ground. Boo Boo yells down, "We need a jar of water up here. It's hot as hell." Beatty says, "Throw down a rope, and you and Sebi can haul it up." Clearly, the alternative is to walk up the ramp, which is now over 500 feet long, carrying the water. Obviously, that ain't going to happen. Later, they're raising and lowering all kinds of miscellaneous items by rope, while the blocks are going up the tortuous ramp. And as days go by, Boo Boo, Beatty, and Sebi improve their system by installing a wood track, initially to keep the pyramid from getting scratched, then a wood crossbeam to pull the rope over, and finally a primitive dumbwaiter to haul up bigger and more varied loads, and to lower unwanted items, like night soil. Clearly, any engineer worth his salt would think, I wonder if we could pull those big-ass blocks up that way. He would then proceed to design something just like what I propose here. This should have been done on the first pyramids and been solved long before Khufu. In fact, solving these types of problems in other pyramids is what probably made Giza possible. But then, who knows, maybe the ancient Egyptians were as stupid as Egyptologists say they were. The advantage of a wheel as a bearing over Lunar's axle bearing is that the distance the axle frictions with a copper bearing is decreased by the ratio of the wheel radius to the axle radius. Thus, if the axle radius is 1 unit and the wheel radius is 7 units, the friction of the axle on copper is reduced to 1/7. The pressure vector on that axle remains the same. Just the distance it must traverse to get the block up the side of the pyramid is cut to 1/7, because the rope pulling the block is not traveling in a 1-to-1 correspondence with the axle, but now in a 1-to-1 correspondence with a larger wheel. Mr. Loner knows this, of course, but he can't make a wheel or the pundits will cry foul, and he wants to be taken seriously by them, so he tries to get away with just the axle, or as he calls it, a rope roll. I, on the other hand, will never be taken seriously by any Egyptologist, or even noticed, so I can say anything that I think is rationally expected of the ancient Egyptians. My opinion is that they had just as much native brain power as we. I'm going whole hog here, so I'll have roller bearings in my wheel too. The rollers are very large diameter things, and the axle bearing assembly is rapidly replaceable by simply taking the weight off and pulling it out of its support cradle. My wooden roller bearings are fabricated on a lathe. Now, Egyptologists will groan when I say lathe, but they can make a lathe very easily, and they can use power tools too. My carpenters have power tools. They're just not electric. They're oxen-powered or people-powered. And I've also designed a telephone system and a telegraph system for communications, and air conditioning for my rest and relaxation tents, and there will be a restaurant on my pyramid with an excellent starlight view of Egypt, and for the kids, Saturday thrill rides on Khufu's Death Dare, the world's first amusement park ride. I don't necessarily think that ancient Egyptians had these things, but they were certainly available to them for only the mental effort. The largest pyramid is actually the culminating pyramid at the tail end of the Imhotep line of engineers. That is, the engineers of Khufu's pyramid were the grandsons and great-grandsons of people who worked with Imhotep, building Djoser's pyramid. Imhotep was a commoner. Djoser must have understood that if you allow commoners into advanced positions, you have a much larger pool of talent to pick from than if you only allow talent from the elite group. I've changed my mind about the wooden wheel rollers. I'm making them out of copper. Solid copper cylinders about 2 inches in diameter and 6 inches long, and they'll roll between 2 copper sleeves about a ½ inch thick. Molds are made from wood models, and liquid copper is poured. Now that's whole hog. Now that we have a viable heavy-duty wheel to act as a bearing, we need to design our sledge to take the blocks up the side of the pyramid. My pyramid sledge is just a slanted but very heavy-duty dumbwaiter. The two ropes to haul it up are attached at the front of the sledge. It goes to the top and the smaller sledge to which the block is attached is pulled off. When the haulers feel the weight removed, they lower the sledge to get another block, which is patiently waiting the return of the sledge. Now, when you've gotten to the top, you could remove the block on its transport sledge and haul it anywhere on that level. I gave some thought to letting the 200 men at the base of the pyramid haul the stone to the other side of the pyramid, unloading it nearer to its final destination, but in the end rejected the idea because it was too easy for the men at the base of the pyramid to move the block over flat terrain. The productivity loss was that the haulers had to walk an extra couple hundred yards for every block, and the accumulated walking was a waste of time and energy. For hauling blocks, any non-pulling walking should be eliminated wherever possible. If they aren't hauling, they shouldn't be walking around in the heat, wasting their energy. If they aren't working, they should be sitting, resting, in the shade, with pretty girls fanning them. So some few guys at the top would have to haul the transport sledges back to the other side of the pyramid to be unloaded, where they'd be set in place. How many men are needed to pull up a block? My calculations are based on the mid-level of the pyramid. It's about 115 meters square at this point, and has about 3¼ acres of open space. That's about 11,000 square meters. I'm going to use 400 men on each track, with 25 tracks total, 200 to haul the blocks up at one time. For every track, it's 1 hour on and 1 hour off to rest. So we have a total of 10,000 men available to haul the blocks up to the top on 25 tracks. The rate of block output is about 4 minutes per block per track. So for a 10-hour day, we get 150 blocks per day per track, and our setup then pulls up 3,750 blocks each day. Note, this is for the inundation period when lots of young bucks are available with time on their hands. This lasted about 4 months, June to September. So that's about 120 days, minus 16 Saturdays off, and 20 days travel time back and forth. And we get 84 work days, times 3,750 blocks equals 315,000 blocks per inundation period. To calculate the force required from each individual hauler, we need to add the weight of the block, the weight of the up sledge, the small transport sledge to which the block is attached, and the friction from sliding on the wood rails. If the weight of the block is 5,500 pounds, that's 2.5 metric tons, and the weight of the sledges is 500 pounds, we get 6,000 pounds. But since the unit is on a 52-degree incline, we reduce the weight figure by 21% to 4,740 pounds. Dividing 4,740 by 200 men, we get 23.7 pounds per man. Similarly, we can reduce the friction by 38% because of the incline. So if the frictional force at ground level required 10 pounds of force per man for 12 men, it would require an additional 1 pound of force per man of the 200 at ground level. A trivial amount, so we really don't require any oil on the track going up the pyramid. Oil would stain the white Tura limestone anyway. This means that each man at ground level would have to pull, or rather push, hard enough to raise about 25 pounds up, and he would have to push for less than 2 minutes to get the block to its destination from ground level, because he'd have to walk on the ground maybe 100 yards. Then he'd have to walk back 100 yards to reset for the next block. And he'd have to do that 15 times each hour for an average walking speed of less than 2 miles per hour. Note that of the 4 minutes hauling time, less than 2 minutes is spent hauling the block up, and the same is spent lowering back the empty sledge. So for most of the 4 minutes, The workers are hauling essentially nothing per man. There is a turnaround time for loading and unloading the block, but that's measured in seconds, so I left it out of the basic calculation. The workday is 10 hours, but the shift is only 9 hours. That's because there are 2 shifts of 200 men per track. So 200 start at first light, and the second shift starts 1 hour later. Each shift puts in 5 hours per day at the pulling station, with 4 one-hour rest periods. Or there could be a morning shift and an afternoon shift, or 4 3-hour shifts, or, well, you see there are many different arrangements possible. In the summer, there are more than 12 hours of daylight, so have at it. This might seem like an easy workday, but each man would have to walk about 10 miles per day. That's not too bad for young people who are used to walking a lot. I personally couldn't handle that much walking. I'd want an electric cart. My guys who are resting from hauling can eat at the barbecue pits, get a massage, play games at the rec center, or take a nap in one of the air-conditioned tents at the rest area. And while they are hauling and sweating, the spritzer girls hose them down with sweet-smelling water and give them drinks and dates and encouragement. These blockheads are pampered beasts of burden. At the end of the day, all workers are required to bathe, and perhaps have their tunics and loincloths washed before they can go home, or to party down at the Pyramid Club. And they have Saturday off. No pyramid work on Saturday, no way. At these rates, and working only 16 weeks per year, the pyramid could be finished in maybe 8 years. There's a lot of leeway in here, but I don't see it taking a full 20 years. At the base of the pyramid, there is a staging area where men hauling blocks from the quarries drag their blocks over wooden rails, and when an empty pyramid sledge arrives, they haul their block on top of it and release it from their hauling ropes. Immediately it is hauled up the pyramid. About 3 minutes later, the empty pyramid sledge returns for the next available block. As you can see, this setup is dirt simple. At the base of the pyramid, the ropes pulling the pyramid sledge are in channels underfoot, so transport sledges can be dragged over them. The pyramid sledge is level with the ground, so the transport sledge just slides onto it, and at the top of the pyramid, it just slides off as easily. From a physics standpoint, it is important that the block should be raised to the top in the least reasonable amount of time. When raising a mass through a gravitational gradient, we have to supply energy equal to the potential energy gained by the mass, plus the hovering energy that cancels out gravity for the time during which the mass is being raised. Think of it like a rocket that goes to the top of the pyramid. If it goes up fast in, say, 10 seconds, it uses little energy. But if it goes up very, very slowly in, say, 8 hours, it could use up all the rocket fuel in the world, exhausting it on hovering energy. Up top, there are tracks going out to all points of the pyramid work area. It would not be easy to drag the block sledge over rough stones. The footing on these stones might be fairly hazardous, since there are gaps between them big enough to swallow your foot and break your ankle. Perhaps these gaps are filled with sand and rubble. I've never seen the pyramids, and I can't make out fine details from the pictures I find on the internet. From what I do see and read, it appears that the blocks are mostly taken from the same bed in the quarry and have the same thickness on each level, except for the one sticking up a few inches to interlock with the next level. This was done to keep the levels from shifting relative to one another during earthquakes. The facing blocks were laid first, and the general body blocks were placed in the best possible fit mode. That is, an engineer would assess each block on the fly and say, "Put that one over here, Sakwi." They do not appear to have been placed relative to one another as they were in the quarry from what I can detect. And that wouldn't work anyway, because of the principle of cumulative slop, which means that the accumulation of small errors in placement make accurate planning from block number 1 to block number 5,000 impossible. I've devised many machines for removing the block from the sledge and transporting it a few meters to its placement site. There is a frame walker which picks up the stone, and you walk it to its destination like a tall ladder, moved from one side of the room to another. You don't lay the ladder down, you walk it. Then there's a simple crane where a group of men counterweight the block and swing it into place. And there's a levering along the floor, rock on rock, or dragging it with ropes, rock on rock, or pulling it into place with ropes from the next level that's being added. I also devised walkers operated by one or two men, utilizing a pendulum effect when the block is swinging, but rejected it because it's too complicated. But the most promising device was a long lever that allows two men to rotate the block back and forth, while another guy pushes the block into position. Imagine a block near the top of the crown of a concrete roadway. If we keep twisting the block back and forth, it will inevitably slide down the crown into the ditch by the side of the road, just by gravity gently nudging it in that direction. Similarly, one man pushing in the desired direction on the pyramid takes the place of gravity and easily pushes it into place. I've devised some adjustable ground levers to push an inch or two at a time that push off in the cracks between the floor blocks. This is not hard to do. The levers they show in animations are a real hoot. They're only good for laughs. For a lever to work easily, it has to be backed up to something solid in such a way that it can't slip. Since there are so many tracks, they simply extend to the far side of the pyramid, and the block is delivered very near its final resting place. When the line of finished blocks gets near the track, it is gradually dismantled and taken up to the next level just made, and installed there for use on the next course. Here's some wood track pieces from the top of the pyramid. They have to interlock without pegs or wheels for fast assembly and disassembly, and they should all be identical if possible. The people who stay around all year I call the hardcore. These are the skilled craftsmen who get paid, and their families. When the annual inundation comes, 10 to 20,000 young bucks descend on the Giza plateau to do the bulk hauling. I call these easy core, and along with the young bucks come loads of single women who do all the cooking and cleaning and the light girly work. Easy core doesn't get paid. It's an adventure, getting away from the farm to see the sights and meet literally thousands of single women. And the women come for just about the same reasons, adventure and to snag a husband. All the young people don't go every year. There's not enough room for them if the population of Egypt at that time was 1.5 million people, and the life expectancy was maybe 35 years. By the time they get to Giza, their life is half over, and they're only 20 years old. Tough life. They died like flies from waterborne diseases, malnutrition, snakes, crocs, hippos, and just plain general mayhem. On the side of the pyramid, opposite the main block hoists, are more hoists that deliver materials and men to the top. A number of men fill gaps in the line of blocks forming at the ready line. This happens because the blocks are not placed consecutively, because this would limit production to about 1 block placed per minute, or only 600 per day, but rather concurrently from 25 different track lines. They can't fit perfectly as they would if placed consecutively, and the larger gaps have to be filled with rubble that's sent up the opposite side hoists. They take down unneeded used materials as well. The small sledges are stacked and tied down, then sent back to the quarries to be reused. Big jars of shice, piss, and garbage are sent down as well, and injured personnel to the hospital. Those with a mathematical bent will have noticed that if the pyramid is at half its height, then this must be the last year that Easy Core is going to work on it. Clearly, a pyramid 1/2 as tall will have a volume of 1/2 cubed, or 1/8, and 1/8 of 2.5 million stones is 312,500, and we've already established that Easy Core can put up 315,000 stones in a short summer season. So there is no more work to be done after this year. Actually, many would be sent home early because there is less room to work as the courses narrow as they go up. The last 30 of the 210 courses contain only a total of about 7,000 stones and would be set exclusively by hardcore. So all of easy core is gone by then. They're involved in only courses 105 to 180 for the last year, and then only a few are left by course 180. They've spent 7 full summers on the lower courses 1 through 104. To place the final level of blocks, hardcore would make use of a crane along with the standard dumbwaiter lift. The crane is mounted on the last track of the opposite side hoist. It consists of a very long sledge with a block on the lower end to act as counterweight, and a wheel bearing on the upper end to which ropes are attached, which hoist the last blocks. The last stone, the pyramidion, is also lifted this way. However, at that point, a working platform, supported by the last 2 remaining tracks, is also built around the apex to accommodate more workers and religious officials, and maybe the pharaoh himself. The 40 to 50-ton stones that make up the king's chamber and grand gallery are lifted to their positions 1 level at a time by means of the rock and chock method. They are roped to these rockers, and as the stone is rocked back and forth, a piece of wood is stuck in the available space. This is a tried and true means of raising such blocks. The effort required is minimal, and an experienced team could lift a 50-ton rock to the next course of the pyramid in no more than 2 minutes. For the estimated 90 blocks, they could raise them all to the next level in a day or 2 with little problem. All of these stones are in their final positions before the mid-level of the pyramid. The greatest pyramid construction error indicative of stupidity is the fact that they were created at all. Truly, these people must have been real retards to buy into any religious plan that required so much effort for no tangible gain. But that's a given that anyone can understand. The actual construction errors require a look at some basic engineering principles. Here are 4 upside-down glasses. One contains water, one contains sand, one contains small rocks, and the last one contains 2 cubical blocks. When we pick up the glass containing the water, it falls down completely. We can say here that all the liquid vectors that were formerly blocked have been released. Thus, all the down vectors from gravity get converted into sideways vectors, and the water spreads. This is why a tsunami can't come in like a pyramidal wave and travel inland. Water falls down. A tsunami comes in like a fast tide, flat and rising rather than running tall. When the glass containing sand is picked up, the sand starts to do what the water did, but is stopped because its liquid vectors get cancelled by opposing vectors which stick by friction and can't convert completely into lateral vectors. The resulting pile is said to be at its angle of repose. The glass with the small rocks falls too, but has a higher angle of repose because it is easier for opposed vectors to get cancelled when there are less randomly shaped pieces touching. The last glass, when raised, results in nothing happening because there are no liquid vectors present in the blocks. They are suspended by the shape of the block. If the 2 blocks touched along a slight angle with respect to the gravitational gradient, there would be cancelled liquid vectors. Now, if we look at the basic pyramid construction at Giza, we see that all the blocks are made of cubes whose faces are all perpendicular or parallel to the gravitational gradient, indicating that they are intended to be completely suspended. The pyramid can't fall down unless blocks are moved laterally, considerably out of place, as in an earthquake. We can then assess the grand gallery as being incorrectly engineered because the stones that make it up are set at a slant. They are in fact cancelled vectors instead of suspended vectors, which would have been the case if the gallery's corbelling were parallel to the ground. This wouldn't look as good, so they did bad engineering here. The pyramid is weak in the direction of the slant. That is, in an extreme earthquake, the side of the pyramid would puff out as the grand gallery block slid down and forced the north face out. Fortunately, this hasn't happened yet. The so-called relieving chambers over the king's chamber are profoundly bad engineering. Given that a flat ceiling was desired over the sarcophagus, the correct procedure was to do a Lincoln log double corbelling. This would fix any problem with weight, because the flat ceiling could then be made freestanding and have no pressure on it whatsoever other than its own weight. Instead, they made the stupid thing that non-engineers think is so clever. This is probably Hemiunu's screw-up here. He's the king's cousin, in charge of everything. I can picture the other engineers saying, "I told you so," when it cracked, but there is nothing they could do because he's the boss. Look at the statue of him. Look at the man boobs. This is undoubtedly a flattering statue. He probably spent more time eating and fornicating than engineering. By far the worst error in the pyramid probably wasn't due to Hemiunu, but to the inability of the architects to understand how to shape the facing stones. They are all made incorrectly. Here's the proper shape. The fact that they are all flat on the bottom is a real boner. This allowed them to slide out of place during the 13th century earthquake, and many fell to the ground, ruining the appearance of the pyramid. This was fatal to the outer casing, because the pyramid was a showpiece of any ruling potentate who laid claim to the pyramids. No autocrat will let you deface the pyramids, since they were his property. But after they were fallen, they couldn't be replaced, so might as well use them to rebuild Cairo. And then, since the pyramids now look bad, let's take them all. It's easier than quarrying new stone. So they're almost all gone, thanks to the boneheaded error of the original architects. There are plenty of other inscrutable things wrong with the pyramids, but as you can see, maybe the Egyptians were as stupid as the Egyptologists say they were. I can't say for sure. This 1,000-plus ton obelisk was abandoned because it cracked during quarrying. Looking at the area it lies in, and conjecturing that they intended to float it up the Nile and erect it somewhere to the north, makes one think, how did they intend to accomplish this? Clearly they wouldn't have begun to quarry it unless they already had a plan to take it out of the hole it was in, get it to the river, transport it, and then erect it. What were their means of doing this? The least energy mechanics for this project would be the sand rocker method. This is similar to the rock and shock method used to raise the 60-ton blocks up successive levels. The sand rocker consists of solid, heavy-duty rounded wood rockers placed all along the underside of the obelisk. On top, there would be an overhanging deck. People on top of the deck walk back and forth in unison as others fill the pit with sand. The rocking obelisk will then rise slowly out of the pit in the manner of rock and shock, with the sand filling the duty of their wooden shocks. If the pit was watertight, water may have just covered the sand, so that in sloshing back and forth as the obelisk rocked, the sand would have been deposited under the rockers. Once the obelisk is up high enough, a ramp is built of wood, stone, and sand, along which the obelisk can be walked to the water by the same rocking motion. There is no danger of the obelisk rolling over if the rockers are made correctly. The ramp has a slight incline that goes to where the water will be when the annual Nile flood comes. To get the obelisk started downhill, one end is raised by rocking and throwing sand under that half. As the end rises, the whole obelisk will begin to move slowly and safely down the ramp as it is rocked. It doesn't take thousands of people, just several hundred, and lots of patience. It is delivered to a pre-constructed dock that will be inundated by the flood, where it is attached to 2 barges utilizing the truss deck. When the flood comes, the obelisk is floated while submerged in the water. The reason for leaving the stone submerged is that underwater it will weigh 37% less than above water, making it easier to handle. This presumes that the Nile at flood is not too shallow for the draft of the boat. If so, it would have to be carried above water in much larger barges. The obelisk may be carried at a slight angle, corresponding to the inclination of the ramp. When it arrives at its destination, we wait for the flood to end, and the obelisk ends up on a prepared dock, which is now high and dry. Now we have a difficult problem of hauling the obelisk uphill to its destination. There are 2 possibilities here. The first is to construct a ramp section and raise the obelisk to some height, on which it runs uphill by going downhill, as shown. The difficulty here is that it is time-consuming to keep raising the obelisk and building a ramp ahead of its movement. A faster way is to use ganged frame walkers along the obelisk, which lift it up while attached to a sledge an inch off the ground. As the frame walker arcs over, the obelisk is advanced perhaps 10 feet with each haul. The design requires that all the frames be on a separate sledge that is advanced alternately with the obelisk. I made some calculations and concluded that such a device would be about 10 times easier to use than a straight-up haul, and that the frames would have a weight approximating 5% of the weight of the obelisk. This procedure would require hundreds of men, but many less than a straightforward haul. When the destination is reached, the obelisk is raised on one end a few degrees until it slides forward to its prepared base. 2 stones arrest its progress. These stones are pivotal. 2 holes are cut into the base and filled halfway with loose sandstone. 2 blocks that fit into the holes are then placed on top of the sandstone, such that they are partly in and partly out of the hole. It is against these 2 stones that the obelisk pivots when raised. As the weight of the rising obelisk presses down on these stones, they crush the sandstone and recede into the holes. Thus, the obelisk can't slide on the base during the early stage of the raising. To get it up, we construct the pictured device, which is half a wheel in principle. On the other side of the wheel, a sand ramp is constructed, and on this a heavy wooden ramp is loaded with small stones until the weight on this side is greater than the weight of the obelisk. The sand under this counterweight is then gradually removed, and as the counterweight drops, the obelisk is raised. The process must be repeated several times, so, when the counterweight goes to the ground, a sand ramp is made to support the obelisk at its new position, and the counterweight is reconstructed higher up. At the final stage, the obelisk is rigidly connected to the counterweight, so that when the sand is removed from under the counterweight, the obelisk will gently go to its upright position, rather than plunking over with a thud, with possible damage to its base or lower corners. Now everything can be removed, and a scaffolding constructed for artisans to carve the artwork on its sides. The entire operation is readily doable by the ancient Egyptians, if they are smart enough and patient enough. How the pyramids were built is not written down anywhere, yet there are pictures of everyday life in the tombs of many people. Therefore, it must be concluded that there was a consensus that no such depiction should be made. Perhaps the pharaohs ordered that no pictures were to be made, or maybe it was considered bad juju to do that. At any rate, the absence of pictures of pyramid construction was not because they just forgot. They couldn't possibly forget something that big. Somebody told them not to make pictures, and they complied. Trying to figure out how the pyramids might have been built is a fun thing to do, kind of like an intellectual vacation, because there's no heavy lifting.